The speaker today is Sarah Klopp. Klopp is from Oviedo. Was physical physics at the University of Oviedo, and then did the PhD in the University of Santiago de Compostela, the group of Vicente Pérez student, who's well known for some of us. And Stefan did the PhD 3 weeks ago.
Yeah.
And now she's with us. She's in classes study these things of Lagrangian problems in the ocean. She will talk about essentially about distillation of plastics in the surface of the ocean. Okay.
So thank you to all for coming. My name is Sarah, and I'm going to introduce you a small part of the results of my thesis, which are the Lagrangian transport of floating plastics in the ocean. So first of all, I want to explain why we choose Lagrangian transport, which are the dynamics that the plastic are subject of, and what are my main objectives. Spoiler, it's validate a new Lagrangian tool and also apply it once it is validated. So the Lagrangian transport differs from the Eulerian ones because here we account for the trajectories, and also other magnitudes that can be followed as a trajectory. So we have a temporal spatial evolution of not also the trajectory, but also other magnitudes such as temperature, speed, pressure, and so on. So in the case of Eulerian aspect, we focus on the grid cell and the temporal evolution of the grid cell, but here we have some extra information. So for the case of plastics, we can consider that it's a Lagrangian transport problem based on the Stokes number. The Stokes number measures the coupling degree of a body with the flows in where it moves. Let's take 2 examples, which are an empty plastic bottle with a cap and a heavy container. If we throw a plastic bottle in the ocean, it rapidly couples to the flow, moves with the flows. That this time that the particle takes to couple with the movement of the flow, it's the time, the tau sub p, the couple time, and it can be related with the velocity of the file and the characteristic length of the particle through the Stokes number. The case of the heavy container is very different because it's an inertial particle. It has a weight that makes the particles not only move because the currents, but also other inertial forces. So consider this Stokes number. When it is lower than 1, we can assume that the particle is a Lagrangian particle. And for us, all our plastics will be Lagrangian particles. We are not keen on other type of particles like plastic bags or heavy containers. These other particles are inertial and they are out of the scope of this study. So there are many different ocean processes that can influence the movement of the particle. They can be divided by scales or in larger scales, which are the typical years of the ocean, and the submesoscale ocean process, which are between 1 kilometer and 10 kilometers. Other related with the wind action, which are this Langmuir circulation, and also the windage. I don't know what are represented the windage, but also these plastics can fragment and sink to the bottom, and also have a vertical movement because the waves action. Also, we should consider the tidal effects and other effects that sometimes is easy and others is not, such as the river inputs, the biological transport, and the ice transport. So the studies I'm going to present here are in the local domain, just for validating. We are talking about 200 meters of resolution, and then we move to a global domain around 9 kilometers of resolution. Which kind of strategies we can use to track to account for the plastic in ocean? Well, we have monitoring collection, which are visual studies. Sea collection consists of in the trawling and beaching collection. We also have image techniques based on satellite images and thermal infrared, but with these tools, we just can't account for the surface plastics. The drifters also, with them we can study the dynamics of a particular region and also the convergence regions. And we focus just on numerical models, which are Lagrangian tools. So first, we want to validate the MOHID-Lagrangian tool, which is a recently developed Lagrangian tool, which is developed in the Instituto Superior Técnico de Lisboa. And we compare the results with the data collection on beaches in the local domain of the Ria de Arousa in Galicia. And then, after it is validated, we apply this model to a larger domain, which is the North Atlantic Ocean, once we define some sources. So the MOHID-Lagrangian is a Lagrangian tracer model, which is able to include different kind of sources. We can also focus on different sink regions and parametrize different type of particles. It's able to include different model inputs of other hydrological models. And the trajectory of the particle is obtained as a sum of the velocity of the particle and diffusivity coefficients, which account for the higher resolution effects that are not well defined in our original resolution. The velocity of the particle can be function of the hydrodynamics, wind, waves. Here in this result, we just consider the hydrodynamics. And this model also presents a robust pre-processing and post-processing tools. So these are simple schematics. Once we determine the type of particle we want to simulate, in our case is something like that, we can give to this particle some properties such as position, shape, size, and density. And as we cannot define the exact geometry of the particle, we parametrize this particle with a spherical approximation. Then we can choose the different kind of processes that influence the particle, and also if it can sink or beach. And sorry, because now it's gonna disappear. I'm not so used to the template. I don't know what works like that. But our study focused on Galicia, particularly in the Ria de Arousa, which is that one, located in the Rias Baixas. And the red polygons are the mussel rock polygons, where the mussels are cultivated. And in the time period we are developing this, during the season that we are running our simulation, the current does something like that. It enters from the south to the inner part of the Ria and go out, flowing through the north, to the north. And why we choose the Ria de Arousa? Because it's the most productive Ria in the Rias Baixas of Galicia. What is a mussel rough cultivation? Well, this is something like that. It's a wooden structure which is in the surface, and from it, there are some growing ropes. These are the growing ropes, and there are placed the mussels to grow, and every 30 and 40 centimeters, a mussel peg is placed in order to relieve the weight of the mussel once it starts to grow. These are the master peg, which are the similar to a pen. And for us, are a perfect and pure Lagrangian tracer because we know the start release location. And we also know that the time that it takes from the origin to the beach is not so long to provoke the degradation of the particle. So for this, we ran 3 simulations. The first one is of 1.5 years, just to know how the marine litter, can distribute along the Ria coastal line. For that, we just set a beaching factor of 80%. The beaching factor accounts for the potential retention of a coastal line. And that's because the Galician beaches are a little bit complicated because they present these rocky areas, intertidal rocky areas, that also influence the retention of the beach. So in some way, we have to consider this effect, and the beaching factor allow us to determine that if a beach can retain more than another. But this is not so easy. And the conclusion of the retention are not presented here because are a little bit complex. Then we also ran another 2 simulations from October to April and October to March, coinciding with the beaching collections. And for this, we just we consider 20, 50, and 80% just to account for different retention parameters. We fit the model with the MOHID hydrodynamical files from Meteo Galicia.
Sorry, Sarah, about the beaching factor, you mean that if some particle goes to some distance of the beach, then with a 0.8% of probability, it's captured? Is this what you do?
You also have to add a level parameter to account for the bathymetry and to know which are your bottom and how the particle can be retained on the sample.
And what's the distance? Do you take to consider the closeness to the coast?
1 meter. 1 meter. Sometimes, depending on the resolution, it's quite difficult to account for the distance, the exact distance. So for the general simulation, we found that the most dirty regions is this one, the Boiro and Pobrado Caramiñal region, and also the intermediate zone of the estuary. The cleanest one region are the most exposed to the ocean action, and also this region that are screened out by other coastal lines. We also want to account for the external source in the case that this plastic muscle peg could come from another areas, and we place 2 polygons of the same size of the bigger polygon in this area. One's in the top, another in the bottom of the area, and we found that just around 30% of the total accumulation comes from these external regions. Moving now to the comparison, here is the Illa d'Arousa, which is here, this one. And here I present the navigation card. As you can see, this green shadow region are these intertidal rocky areas. So it's going to be difficult, but we found that for most of the region, we can find a similar trend on accumulation. Here, all the results are relativized to the maximum accumulation, and in yellow, pink, and blue, we present the 20, 50, and 80 beaching simulated results, and in purple, the monitoring data. So for most of the cases, we found that they match in a very accurate sense. Let's take the example of S1. We found that this is the most dirty region of all the Illa d'Arousa, and this behavior is also well reproduced by the model, and also for the S2, S3, S5, 6. But we have 2 disparities between the segment S4 and S9. And if we make in the case of the S4. This is the computational reproduction of the coastal line, which differ a little bit of the real situation. All these brown dots over the sea are the mussel rafts. So this region is likely to suffer this accumulation in this beach, but because these ports, these boats along this region, it's quite difficult for the particles to go out again. So maybe this can be the explanation for this disparity between the monitoring and the simulated data. And if we move back, the S9, here we have more accumulation given by the model than the reality. And that's because this bridge join the island with the rest of the area, and it divides this part of the area. We can expect that these two segments have the same behavior, but if we move to the island in a windy day, in this part of the area, in the north part, we found that there are a very windy condition that enable to us different windy sports, but that's not the same in the south part in the same day, because this bridge screen out this wind effect. So less particles reach the south part than they do in the north part. But the model sometimes can see these effects. So here is the disparity. And if we move for another beach collection along the Ria coast, we found again similar behavior for all the beaches, but we found a disparity again in the Carreiro beach, which is this one. This is a beach which is totally orientated to the go out of the particles. So it's more likely that particles stop here than in the other. So for this, in the reality, we found a high monitoring data, but it's not the case of the simulated. But so because sometimes the orientation of the beach is quite difficult for the reproduction, for the computational reproduction, and here we found these disparities. And now if we move to a global domain, a higher domain, here we have this is not the Atlantic meridional overturning circulation, sorry. That's for the thermolink. This is the subtropical subatlantic year. And if we particularly focus on the Bay of Biscay, the Gulf of Cadiz, and the Alboran Sea, we have a different behavior between cold and warm season, because during the warm season, cold season, we have an eastern and north current, which in summer it's a counter current. And also in the in the Gulf of Cadiz, we have a jet moving most of the water masses through the Mediterranean. I explain this because it's important for the final results. So here we don't have any real data or any real knowledge about where are the exact points of emissions. So we choose 3 potential emitter points. Ones are the rivers, which are 70 points along the Spanish Atlantic coastal line, which follow the river discharge, and also they are waiting between them, because it's not the same that the river basin is high or low populated. The highest populated, the highest potential plastic to enter in the ocean. And for the online point, we select 18 points following the MAPAMA and FedEx strategy maps, which measure the potential pressure in the pollution of accounting for bathing areas, coastal ports, wastewater management plants, and others. And for the marine traffic, as it's very difficult to know what's the exact point of the emission, we cover all the marine traffic route, which is this profile parallel to the coast of France, Spanish, and Portugal, with a polygon type emission. So for the rivers, we have a point type emission, which is variable on time because we know that the river flows can influence the entrance of plastics. And also we weight the different rivers between them because it's not the same ones or another's. For the online points, we also choose a point type meters, but here we cannot establish any variable rate. What we want to do is an statistical study. We are not interested in the exact behavior. We want to set, well, the 80% of the particle that I emit here goes to there. And for the marine traffic, we set a polygon type. So we define a polygon at time at KM6 polygon, and we establish a resolution to emit the particles dentro del polygon, in the polygon. Here we don't weight the emission between them. We consider all of them equal potential to emit particles, and here we measure the concentration and also the seasonality. For the point sources, we can also measure the dispersion because we have a lat long initial point and lat long final point. So we ran a 7-year simulation of 1 day of temporal resolution and 9 kilometers of special resolution following the key MEMS hydrodynamic field input. Here, as we were not keen on the retention of beaches, we set a 50% beaching factor, an arbitrary beaching factor. And as we said before, we measure the relative accumulation, relative dispersion, and seasonality. If we plot this in relative terms of the mean relative concentration area, again, we relativized all the concentration to the maximum time. We found this in a local domain, but also we found that the particles can reach the mid of the North Atlantic. Well, the most contaminated area is the Gulf of Cadiz. That's because the Guadiana and the Guadalquivir plays a very important role in contrast with the rest of the rivers. And also there are some contamination in the north coast of Morocco because the west and east Alborán years. Lowering the online contamination or the online accumulation. Well, we found a highest accumulation in the Bay of Biscay, and the contamination that we found previously in the case of the rivers, it's reduced here in the Gulf of Cadiz and also in the north of Morocco. And for the marine traffic, this contamination or this accumulation in the Bay of Biscay is highest, because here we are also consider the French contribution. But this is just a plot of 7 years accumulation, so we can take other measures such as the relative dispersion. Since I know the initial state of the particle and the final state of the particle, I can measure the dispersion on longitudes and latitudes. For this, I group all the meters of the north of the peninsula, the Iberian Peninsula, the emitters in the south part of the Iberian Peninsula, and the emitters in the Canary Islands. Here I present just the online points, but we consider also the river emissions for these statics. And in the case of the north and south emitters, because the semi-enclosed area, we found that the movement is more pronounced in latitudes than it is in longitudes, and that's for this following the shape of this base. And in the case of the Canary currents, we found a more elongated behavior because the particle released in the Canary Island follows the Canary current and flows parallel to the equator. Moving now to the seasonality, as we know the track of the particle, we can also extract the information for each target region. In this case, I just plot the particles in the B of Bisky, and we can measure the presence of particles in the B of Bisky of each stars. Sorry, they are in stars, but we found that during the cold season, during the autumn and winter, the particles released at these points suffer an increase, a deep increase, because this blue current, moves all the particles to this target region. And during the summer seasons, during the warm seasons, summer and spring, this presence decays because this current, and that that movement is the opposite for the French sources. Sorry, during the cold season they suffer a deep decrease, but during the cold season they appear in our target region. So the Lagrangian tools enable to do studies like that. So to sum up and account for the transbordary pollution, for the B of this. Sí, yeah, sorry, yeah, but I'm not presented here. We will use the results of Portugal just for the case of the Portugal. And in relative terms, again, we found that in the B of Bisky, the relative importance of the French and Spanish coast in the north are 50-50, and with a small presence of the Portugal's one, which are the northmost emissions. The case of the Gulf of Cadiz and the Alboran Sea are high related, so I presented the same chart plot. And the highest contribution comes from the south, and that's because we join the south of Spain and the south of Portugal. But if we define here a division for the Algarve, we find a lower percentage for Spanish sources also. And in the case of Canary Island, we find that the highest presence is from the Portugal sources, because all the emission here flows parallel, as you remember, parallel to the Portuguese coast and reach the Canary because the Canary current. And it's significant that there are also a presence of French contribution that are related here in F4, that during the cold season escapes and then is trapped by this current and flows this way. And to sum up some conclusions, so the objective of this thesis was to answer this question: is the MOHID-Lagrangian a useful tool for tracking marine litter? Yes, we can say that in some cases it's highly applicable, but in other ones it depends on the resolution. It's not so well. It does not it does not work as well as in the highest resolution. All the results should show in relative terms, and we also need to define the potential source, and this is the main source of error. And as I said before, the model resolution is very important for our results and for the reliability of our results. So thank you for your attention.
I don't really I haven't captured exactly what is in the first part of the talk. Where do you get the velocity field from?
From the model of MOHID.
So it's the same name as the Lagrangian tool.
Yeah.
So it means, so what are you checking? You have some velocity data from a model. It probably is a model with a simulation, so it's model and data combined, and this is called MOHID. And then you use this tool to advect particles with these velocity fields. What are you checking? Which of the two things are you checking? When there is some difference between the observed release, the observed plastic on the beach, and what the model calculates, do you know if it's a deficiency of the velocity data or a deficiency of the advection scheme? Or
No,
where
we
is
assume that the velocity data is high enough because
it's
it's an
checked?
operational model.
So it's checked independently. That okay, and then still I don't know what is inside the Lagrangian tool. So you integrate you move the particles with the surface velocity field. You don't take into account any wind on the particles, no Stokes drift from the waves. So
No.
so what is just the pure advection by the surface
Yeah,
velocity flow?
when we start to run the simulation, we were not sure about the efficiency of the windage account and the Stokes drift account.
Yes, a last question in the other part with Atlantic. I understand that you only consider releases from specific parts, and then you are only measuring which plastics go from specific parts to final parts. You are neglecting any plastic that comes from outside, from North America, from whatever. Okay. Yes, you're restricting to this, so probably this will not be what you measure on site.
Yeah,
But you are trying to understand sources and destination pathways. Is this the case?
Sorry, can you repeat the?
No, okay. For example, you don't in this plot you don't have Portugal sites on land, Portugal rivers or Portugal on land points. So you are not considering.
No, I'm not presenting the results here, but we consider.
But you don't consider releases from, I don't know, from Norway or from Morocco, from.
No.
So you're only considering releases from specific points to specific endpoints, and you are looking at the sources and destinations between both.
Because this study was asked for the Instituto Oceanográfico Español de Vigo, and they want to just focus on the Spanish emissions.
Thanks.
A technical question. When you use the Siemens aeonic model, this model has 1 day of temporal resolution of 8 kilometers of spatial resolution. And I think that this relationship between the spatial and temporal resolution has a numerical diffusion.
Yeah. Yeah, I agree with you. But for the domain that we want to cover, we need a low resolution model in this case.
No, I mean, because when you compute, when you resolve the equation of motion, in 1 day, one particle can move maybe 100 kilometers, and your spatial resolution is 8 kilometers.
Yeah.
So you need to, I don't know, to improve this part of the Lagrangian model to reduce this numerical diffusion. I don't know if you do something.
No, I'm not working even more in this model.
Okay, thanks.
One. Any comparison with real data?
Yeah.
Of your results?
Yeah.
In the Canary Islands, for example?
No. No, I would like to do it, but it's not easy sometimes to get the results, the real results.
But there are I guess, no?
I mean, there are some data, but it's not easy to find it or to contact with the university to make some comparison. And this kind of comparison needs a high resolution domains. And for me, it's difficult to join the global domain, lower domain. I mean, the particles that flows from the Galician coast, for example, these mussel pegs are found in the Canary Island, but it's quite difficult to simulate the path, the particle from Galicia to Canary Island, because we need a very low resolution, a high resolution domain in the Canary Islands. Because with the KIMEM, some islands are resolved in 4 Richters. So
no. You have a question?
Yeah, can you hear me? Hola? Hola?
y si la escribe, la podemos ver.
I know we have a problem with the loudspeaker here. We don't hear you. Can you write a short question in the chat? And because we have the speaker is not working here. We cannot hear you. If you can write some short question, would be good. Oops, there is a. Well,
Do you think that stocks is important for your problem in enclosed and shallow areas?
Yeah, definitely. In the case of this, in the case of the local domain, it's important to consider and also the wave action.
Okay. Okay.